A very good morning, class 12th. The agenda for today's class is an important topic known as valence bond theory in the coordination compounds, which actually tells you about the bonding in the coordination compounds. You very well know a coordination compound has got a ligand and you have a central atom. The central atom is generally got vacant d orbitals where your ligand donates the electron pair. That is how the coordinate bond is formed between ligand and the central atom, and this is what we would be doing in detail in this particular lecture. You are welcome to the channel by Seema Makhijani. Hope you are enjoying chemistry. I'll try to make the concept easier for you all. Let's now talk about the applications of this particular theory. The first application is it tells you about the hybridization of the complex. Now, if you know the hybridization, you would also know the geometry, you would also know the shape, and you would also know the bond angle. That is understood. The second application is that in this complex, you can also talk about the magnetic character of the complex. You very well know when we talk about magnetic character, it is either diamagnetic or it can be paramagnetic. Now, for paramagnetic, you should have unpaired electrons in the complex, whereas for diamagnetic, all electrons are paired. This is already known to you people that presence of unpaired electron is paramagnetic, while all electrons are paired, that is diamagnetic. So you can find out whether your complex is diamagnetic or paramagnetic. Moving to the third is whether your complex is a high spin or a low spin complex. Now, actually, your easier way understanding is spin actually refers to the unpaired electrons again. So, if it is low spin, it means unpaired electrons are less. And if it is high spin, it indicates that your unpaired electrons are more. Is that fine? Moving to the last application. This last application is it tells you whether your complex is using inner or it is an inner D complex or is it an outer D complex. What do we mean by this? If you have used the inner D electrons, inner shells D electrons, then it is said to be inner D complex. If the coordinate bonds are formed by the D orbitals of the outer shell, then it is called as the outer D complex. Fine. Now we'll go to the steps. The steps to do this theory or to understand it better is, step 1 is you need to identify the central atom. That's point number 1. Second is you need to find oxidation number of the central atom. Fine. Thirdly, now you need to write the electronic configuration of the central atom. Fine. After that, you need to identify the ligand in the complex, whether it is a strong field ligand or is it a weak field ligand. Now, this is new to us. You need to understand this is the key point in this theory. When we talk about a strong field ligand will cause electron pairing in central atom, while a weak field ligand will cause no electron pairing of the central atom. Now, how do you know? I'll give you a small hint. Weak field ligands are halides and water. That's what I am saying. You will not find it in books. I would advise for all your fluorides, chlorides, bromides, if they are the ligands, please take them to be weak ligands and also water. they would be considered as weak ligands and they will not cause any electron pairing. Rest all other than these will be considered as the strong field ligands. So this was the key point which I wanted you to understand. Is that fine? Now, after you identify the ligand is strong field or is it a weak field ligand, then you will do accordingly. Do the needful. इसका क्या मतलब? If it is strong field, pair the electrons. If it is weak field, do not pair the electrons. Leave them as it is. Fine. After that, the sixth point is you will hybridize the vacant d orbitals. Now, why are we hybridizing vacant d orbitals? The reason is we have to form coordinate bond. And for the coordinate bond, as I had told you, the ligand will use its electron pair for the coordinate bond with the central atom. So, the central atom has to have a vacant d orbital or a vacant orbital. Since you require vacant orbitals, so you need to identify how many vacant orbitals do you require in the central atom. Lastly is you will show the formation of coordinate bond between ligand and the central atom. So these are the steps that I would be following. I'll be doing examples now. You can pause the video and quickly take a note of it before we move on to the examples for getting the better grasp of the topic. Before I move forward, just remember that weak ligands will not cause any pairing and these are halides and water are weak ligands. This is the key point of the concept, that halides and water will be considered as weak ligands. Rest all are strong. And what does a strong field ligand do? It causes electron pairing, while these ligands do not cause any electron pairing. Moving on with the first example. What is this example? What is this? This is hexaamine and you have cobaltate, or it will be cobalt. It will be cobalt because it is a positively charged complex. So it is hexaamine cobalt complex. Fine. Now moving on further, which is the central atom? The central atom here is cobalt. Now what is the atomic number of central atom? The atomic number for cobalt is 27. Now you need to find out the oxidation number. The oxidation number of cobalt can be found as, let us take it to be X. Amine is a neutral ligand, so 0, and you have it as equal to the charge plus 3. So your oxidation number of cobalt becomes plus 3. So your cobalt is in plus 3 oxidation state in this particular complex. Now let's write the electronic configuration. I'll first write it for cobalt. The electronic configuration would come out to be argon, 18 electrons, 4s2, that makes it 20, and then you have 3d, how much? 7. That is the electronic configuration for cobalt. But in your complex, the cobalt is as cobalt plus 3, which means you need to remove 3 electrons. Please don't mess it up. Do not remove the electrons from here. The electrons are to be removed from the higher n value. So remove these 2 electrons and you can remove 1 electron from here. So you end up in argon. 4s I am not writing, 3d6. There is nothing in 4s and you have nothing in 4p. You have nothing in 4d. That should be understood. Fine. Now writing the electronic configuration in the box format. This is your cobalt 3 plus. It has got 3d with 6 electrons in it. 1, 2, 3, 4, 5. According to Hund's rule, this is how you will fill up, and 6. Now the next point was, once you are done with the electronic configuration of the central atom, now you have to identify the ligand. Now which is the ligand? Ligand is ammonia. And ammonia is a strong field ligand because weak ligands were halides and water. Since it is a strong field ligand, what is the conclusion? Electron pairing is going to take place. So please pair these electrons. So the next point I am writing is effect of ligand. The effect of ligand would be in your cobalt 3 positive, your 3D would change into 1, 2, 3, 4, 5 and 6. So these two orbitals are now available for bonding. Now how many ligands do you have? You have got 6 ligands. If there are 6 ligands, therefore you will form 6 coordinate bonds. If you are forming 6 coordinate bonds, means you need 6 vacant orbitals of central atom. Now you have 2 here, next would be 4s, 3, next would be 4p. How many? 1, 2, 3, 4, 5 and 6. So the orbitals that you will use up for hybridization become these 6. These are to get hybridized. Fine. So the hybridization therefore becomes D2sp3. That is the first aspect, hybridization done. If it is D2sp3, you have a shape of octahedral. Number 1. Does it have unpaired electrons? No. All electrons are paired. Since all electrons are paired, what do we conclude? It becomes diamagnetic. Since it has no electron unpaired, so it becomes a low spin complex because there are no unpaired electrons. Now, which d orbitals have you used? You have used the inner d orbitals. Your 4d still remains vacant and you have not used it. So, which d are you using? 3d. So, it is a inner d complex. Have I made myself clear? Now what we would do is, we would show the bonding in this particular complex. To show the bonding, you need to now write down the ligands. What are the ligands? Ammonia. How many ammonias you have? 6. So these are your 6 ammonia molecules or the ligands with their lone pair, which is to be bonded coordinatingly with the central atom. Hence, we would form a coordinate bond like this. This is bonded here in this vacant orbital. This is shared with this vacant orbital and so on, so forth. This is how you would show the bonding. And if you are asked to write the structure down, I would advise you write it like this. Cobalt 1, 2, 3, 4. I am drawing the octahedral for you. You will write 6 ammonia molecules. This, but there is a charge which can be written like this to illustrate the octahedral geometry. All angles would be 90 degrees. Moving on to the next example. The next example is potassium hexafluoridocobaltate. So your central atom in this complex is cobalt. Also, if this is your central atom, which is cobalt, what is the atomic number for cobalt? Again, 27. Let's find the oxidation number for cobalt. The oxidation number of cobalt is to be found out. Let's do it. You have, for your potassiums, you have 3 potassiums, so you have +3. Cobalt you do not know, so X. Each fluorine would have a -1, so you have a -6 is equal to 0. Let's find out X. Comes out to be 6 minus 3 is equal to 3. So your cobalt in this complex is also cobalt +3. Cobalt +3, as I had done in the last example, the electronic configuration came out to be argon with 3d6. So I would write the electronic configuration of cobalt. So your cobalt in the +3 state is with 3d6. 1, 2, 3, 4, 5 and 6. Now what is the ligand? The ligand is F-. What type of ligand is it? It's a weak field ligand. If it is a weak field ligand, therefore no pairing. So your electronic configuration remains like this. Hence, Also, how many ligands are there? There are 6 F minus. Therefore, 6 coordinate bonds. Therefore, 6 vacant orbitals for formation of the bonds on the central atom. So, this is your cobalt with 6 electrons like this, no pairing because it is a weak ligand. Now, you require 6 vacant orbitals. Now, these 6 vacant orbitals would be 1, 2, 3, 4, 5 and 6. So, this is your hybridization, that is sp3d2. Now, since this is sp3d2, do you understand you have used outer D's? So, it is an outer D complex, number 1. On top of it, you have unpaired electrons. How many? Since there is no effect of the ligand, you have unpaired electrons, n is equal to 4. Since it is unpaired electrons 4, so it becomes paramagnetic. Fine. Now, let's show the bonding. For the bonding, you require your ligands to be written down. What are your ligands? F minus. How many? 6 of them. Each F minus has a ligand. It is an electron donor. I am showing the lone pair with the help of these 2 electrons as 2 crosses. And now you need to show the coordinate bond formation. So, this electron pair is shared here with this vacant orbital. This here, this here, this here, this here and this here. So, 6 coordinate bonds are formed. So, your complex is also said to be a high spin complex. Why is that? Because of the presence of 4 unpaired electrons. Fine. Moving on to the next 2 examples. Have a look at these complexes. Now, this complex is the anionic complex. This is also the anionic complex. What is the difference? In both of them, the central atom is nickel, and nickel has an atomic number of 28. So, electronic configuration for nickel is going to be argon, 4s2, 3d8. Now, what is the state of nickel in the 2 complexes? Let's find out the oxidation number. In both the cases, you would have x minus 4 is equal to minus 2 the charge. X for nickel, 4 chloride minus 4 is equal to minus 2 the charge. So, your x comes out to be plus 2, x comes out to be plus 2. Both the complexes are same in category. So, your central atom is equal to nickel in plus 2 state. Therefore, the electronic configuration for nickel plus 2 would be you have to remove 2 electrons. Which electrons will you remove? The outer ones. Outer are these 2. So, the EC is argon with 3d8 in both the cases. Now, what is the difference then? The difference lies in the ligand. This has a weak field ligand, that is chloride. Because it has a weak field ligand, therefore, there will be no electron pairing. Whereas, in this case, the ligand is a strong field ligand because it is not a halide or water. So, it is a strong field ligand. Therefore, electron pairing will happen. Now, let's see what would I do. Let's observe the effect of the ligand in both the cases. You have nickel 2 positive, 3d is 8 and this is a strong ligand. So, your electrons will be paired up like this. While in this case, this is a weak ligand, so no pairing. So, you will write your 8 electrons like this. Is that fine? Now, moving on further. How many ligands do I have? I have 4 ligands. Therefore, 4 coordinate bonds. Therefore, 4 vacant orbitals. So, in this case, your nickel 2 plus therefore would be 1, 2, 3, 4, 5, 6, 7, 8. This would be the vacant d orbital. You use 1 from 4s and from the 4p you would use 2. So, you have dsp2 is the hybridization which would be dsp2 in this case. Talking about the other case, in this case also the ligands are 4, but these 4 ligands are the weak ligands. Since they are weak ligands, they will not cause pairing. So, your electronic configuration of nickel 2 positive in this case remains as it is, and you do not have any vacant d orbital here. How many orbitals do you require? For 4 ligands you require 4 vacant orbitals. So, these are the 4 vacant orbitals you will use, and that's the way where we change the hybridization. This goes to sp3. Let's talk about this. There are no unpaired electrons, so this is low spin and it is diamagnetic, and you have used inner D. So this is also, you can call it to be inner D, but in this case it is got a hybridization of dsp2, and when it is dsp2 the shape is square planar, is a new hybridization for you. I'll draw and show it to you. Coming to sp3, when I talk about sp3 there are two unpaired electrons. Since there are unpaired electrons, this can be called as a high spin as compared to this one, and you are using the unpaired electrons, so this also becomes paramagnetic. Since it is sp3, the shape is going to be tetrahedral. The angle is 109.5, whereas if this is square planar, the angle would be 90. I'll just show you the structures now. Now, in a square planar, your nickel is surrounded by 4 Cn minus on the corners of a square, and there is a 2 minus charge on it. This is how you draw this. While in this case, you have got a nickel which is again surrounded by 4 chloride ions, but the geometry is tetrahedral. So the angle here is 109.5 and it also has a 2 minus. I would love to do just one more tricky example. This is your next example, which is your trioxylato cobaltate. Now in this case, what is the central atom? The central atom is cobalt. What is the atomic number for cobalt? 27. Let's find out the oxidation number. X for cobalt, each oxalate has 2 minus. There are 3 such 2 minuses. So you have minus 6 is equal to minus 3. Therefore, X is equal to plus 3. So the oxidation number of cobalt is plus 3. Ligand is oxalate. So it is a strong field ligand. Therefore, electron pairing has to take place. Electronic configuration of the central atom. So in case of your cobalt plus 3, your configuration would be argon 3d6, because you have removed 3 electrons, 2 from 4s, that's it, and 1 from 3d. So your cobalt is this in the configuration, which has d6. The effect of the strong field ligand would be pairing, so they would get paired up and you would end up in this. Now you require how many vacant orbitals? There are 3 ligands, but these are a didentate ligand, which means each will form 2 bonds. So there are 3 didentate ligands, therefore